Hello everyone and welcome back to my channel. In this video, you're going to learn about conditionals and biconditionals. With this video, the overlap between the logic and mathematics will stop, and then only the mathematics will kick in after this. So things are gonna get hard after this class, but that's expected. So in this video, we're first going to cover conditional statements, give examples of that. Second, biconditional statements, give example of that. And then I'm gonna introduce two terms, converse and contrapositive. All right, so before I go over conditionals, let's remember what are propositions and statements, because they're super important. These are sentences that are used in mathematics. So in regular language, we use all sorts of sentences, but statements are a specific type of a sentence, okay? So statements have a very important feature. They're either true or false. Regular sentences that you use all the time, such as, I don't know, I'm tired today, that's not a statement because it can't be either true or false. It's not that type of a sentence. So example, 2 is an odd number, that's a statement. Its truth value is false, but it's a statement because it's either true that 2 is an odd number or false. And that is what makes it a statement. This is super crucial in mathematics because you're going to build pretty lengthy arguments, mathematical arguments, and prove your arguments. And since you're going to use statements as your sentences, then, and they have truth values, they're either true or false, you can track the progress of where you are. So you can draw the final verdict. Okay, so just like in finance, when a company is in a sketchy business and you audit it and you follow the money and see where it goes to find the financial crime, just like that in mathematics, you will follow the truth values of each individual statement and see where the argument leads you to draw your final verdict, whether the argument is true or you're going to disprove it. So that's why using statements that have that feature that they're either true or false is so important in mathematics. So conditionals as well as biconditionals, they are using statements as its building blocks. Just like in the previous video, conjunction, disjunction used statements, same thing as propositions, to build conjunction, right? So here, keep that in mind. Okay, so now let's start talking about conditional statement. So it sounds like this: if P, then Q. Conditional, what comes to your mind when you think about that word? That there's a condition that needs to be fulfilled. Or conditional love. If you do this, then I will do that. Or conditional relationship, right? So that's exactly what it is. And its structure is if something happens, then something else will happen. If X will happen, then Y will follow. So here's an example. If a number is divisible by 4, then it is even. Individually, taking a number is divisible by 4, you can check the truthness of that. Because you can take a number, try to divide it by 4, and see if you can do it, and then you can say it's true or false. A number is even. It's either even or odd. We're talking about integers here. Integers are either even or odd. So that has a clear truth value. So both individually are propositions, and put together in a conditional statement, if P, the first argument, we're gonna denote that with a letter. Some textbooks will use A or B. This textbook uses P and Q. So if P, then Q is what we're gonna say. And with P, we mean the first proposition, and with Q, the second proposition. That's just a shorthand. So conditional sentence, the whole thing, if P then Q, is a proposition itself because we use propositions to build it. And since the whole thing is a proposition, we're going to determine its truth value as well using truth tables. So that's why, do you see how it's super useful? So the first proposition in a conditional statement is called antecedent. And usually etymology of a word is quite useful for memory, so I have it here. Antecedent word means that it comes before something. So the first proposition will come before. So first proposition is a condition. What do you need to do for the second thing to happen? If you do this, then I will do that. The first one is antecedent. The second, consequent, means that it closely follows or comes after something, and it comes after the antecedent. And I just had a dark thought. Don't remember that P is an antecedent and Q is a consequent, because you understand that these are just placeholders. They don't matter. What matters is that what comes after if and before then is what is antecedent. And what comes after then is a consequent, right? So whatever things depend on, what the promise is hinging on, what the condition is, that's antecedent. And consequent is what I promised you. If you do this, then I will do that. Okay? All right, let's go over first example. If you listen to this video, then you will learn conditionals. Okay? That's a conditional statement. Let's first identify antecedent and consequent, as I have done here. Then let's go over truth tables. You can screenshot this truth tables for conditionals and keep it, because every single conditional statement will have this exact truth table, always, okay? And notice that it is true 3 times out of 4, it's false only once. So conditional statement is not as demanding as others you've seen. It's true most of the time, right? So let's go through the truth table line by line and use this example. In the first row, what happened is that you did listen to this video and you did learn conditionals. So the whole conditional statement is true here. Think of conditional statements as a promise and think about, did the promise get broken here? And if it didn't, then the conditional statement is true. In the second line, you did listen to this video, but you didn't learn conditionals. But that was my original promise, that the whole thing that you would learn conditionals depended on you listening to this video. That was the whole purpose of that statement. So if that didn't happen, if P happened, if you did listen to this video, if antecedent was checked off, but the consequent didn't follow, then it didn't come through on my promise, basically. So that's where the conditional statement is false. And this is the only place it's going to be false. Third line is that you didn't listen to this video and you still learned conditionals. And notice that the whole conditional statement there is true. And why? Because conditional statement is not as strict or binding as later biconditional will be. So conditional allows this. Because you might have learned about conditionals from your professor, from your textbook, from other YouTube videos, right? Or from ChatGPT. And that's perfectly allowed by conditional. Because conditional doesn't state that you will learn conditionals if and only if you listen to this very video. We didn't say that. So notice that if antecedent doesn't happen, consequent can still happen in conditionals. That means that antecedent is not necessary. It's just sufficient for consequent. More on that later. Now the fourth line. Fourth line is interesting. It says that you didn't listen to this video and you didn't learn about conditionals. And that, in fact, is perfectly in alignment with the original promise. Because if you want to read it like this, if you don't listen to this video, then you won't learn conditionals. Okay, that's not contradicting the original iteration of the statement. So that is why the whole conditional statement there is true. Sometimes people say that, they find it weird, or they say that, logic is weird, that there are 2 false statements and you're getting a true statement after that. But it's not as if you're adding 2 false statements and the sum total of them is true. No, you're not using conjunction and saying false statement number 1 and false statement number 2, they equal truth. No, that would never happen in logic. You wouldn't want it any other way. If you think about it, this works perfectly. In mathematics, logic is immaculate. So that's one of the beauties of getting to be in this field. All right, let's go over second example. If the weather is warm, we will go hiking. Notice that there is no then here in this statement, but it's still if P, then Q. Sometimes then is omitted, but if you insert it back, the sentence will make sense. First step, identify antecedent and consequent, just like I've done here. Now let's go over truth tables line by line. The first line says that the weather was warm and you did go hiking. The whole conditional is true here. Second line says that the weather was warm, but you didn't go hiking. And that's where you broke your promise, because everything depended on weather being nice, and it was nice and you didn't go, you said you would. So that's where the promise gets broken and their conditional statement is false. Third line, interestingly, says that the weather wasn't warm, but you still toughened up and went hiking. And that's fine. Conditional allows that. Because we didn't say that you will go hiking if and only if the weather is nice. Okay? Again, antecedent is not necessary for consequent in conditionals. And finally, the fourth line says that weather was not warm and you didn't go hiking, which is in alignment with the first original version of that statement. Okay? So notice here what happens when the conditional is false. This is useful because later in your mathematics career, you will need to deny and prove or disprove a conditional statement. And the only way to disprove a conditional statement is to argue that P happens and conjunction, that's a symbol for conjunction, Q doesn't. So you will argue P and not Q, okay? Because that's the only place where the conditional is false. So that's the only way to deny or argue against a conditional statement, okay? Now I will show you different iterations of if P then Q that might be disguised, or you might not recognize that sentence is same exact thing. It's exact same thing as if P then Q. Okay, first one says P is sufficient for Q. Okay, that sentence is same as if P then Q. And why? Because that says that if P happens, that's enough to guarantee Q. First line, you see that. In the second line, P happened, and we said that that's enough to guarantee Q. That's what it means. P is sufficient for Q. And since Q didn't happen there, okay, the whole conditional breaks there. That's where it's false. Third line says that P didn't happen, but Q did. But notice that we didn't say that P was necessary for Q. We only said that P was sufficient for Q. So that's fine with conditionals, that P didn't happen, but Q still did. This would be similar to saying that you went hiking even though it wasn't warm, and that's fine. The final line says that P didn't happen and Q didn't either. Nothing gets violated there. So P is sufficient for Q is the same exact thing as if P then Q, and therefore you would expect their truth tables to be the same. Okay, so I wrote this paragraph for you, which clarifies this sufficient and necessary business. So if you read this after you've done some thinking on your own, then this paragraph will make sense and will help you. But if you read it right now, it might confuse you more. So do some thinking on your own and then read it. All right, so another way that you might see if P then Q is to say Q is necessary for P. Because here what you're saying is that there's no way that P will happen if Q doesn't. So if Q doesn't happen, then P can't happen, is what you're really saying here. And notice where Q doesn't happen, where consequent doesn't happen. There are two lines like that. Second line and the fourth line. And the second line, where Q doesn't happen and P does, the whole conditional is broken there. And the fourth line, Q doesn't happen and P doesn't either. Another way that you could see it is P only if Q, or Q whenever P. Those are same thing as if P then Q. All right, let's move on to biconditional now. So biconditional is a stricter, more demanding, more binding, more intense of a statement. It sounds like that too. P if and only if Q, okay? And it is more demanding. Interestingly, its symbol is now bidirectional. That's where the name biconditional comes. So there's double-sided arrow, meaning you can go back and forth, meaning these two statements on either side of this double-sided arrow symbol are logically equivalent. Meaning, logically equivalent means one thing only, that the truth values of both of these statements are the same. So if one is true, the other one must be true too. And if one is false, the other one must be false as well. It's true twice when P and Q have the same truth value, which happens in the first line and the fourth line. And it's false other two times when they're mismatched. Let's go over the example. And it's good useful to think about biconditional as a really binding friendship pact, really strict pinky promise. So you only go to the gym if and only if your best friend goes too. In a first line, you both went, and biconditional didn't get broken there. In the fourth line, neither of you went, and that's fine. The biconditional is true there. Friendship is safe. But in the second line, it says that you went to the gym, but your friend didn't. In a third line, you didn't go, but your friend did. And that's not allowed in this pact, okay? Because it says that you will go if and only if your friend goes as well. So that's where the biconditional is false. Let's see another way to phrase biconditional, okay? P is necessary and sufficient for Q. Notice that in biconditional, the third line will be false. So P is necessary and sufficient for Q. Before, for conditional, P was sufficient for Q. Now it's necessary and sufficient, meaning that anytime P happens, Q has to happen too, or they both don't happen, okay? Another way to say it is that P is equivalent to Q. And this is quite important because a lot of the times you will see things like two lines are parallel if and only if they have the same slope. Okay, these two statements on left and on right, they're equivalent because they're you see that symbol, which means same thing is also known as same as. A lot of the times when mathematicians are writing on a board, when they're rushing, they will put this expression is same as, and they will put that if and only if symbol there. So two lines are parallel is the same thing as saying two lines have the same slope. Separately, these two statements contain exactly same information, not one bit more information or one less information. So if you give me one of them, you haven't deprived me of information. So you can just say one or the other. Okay? Another way to say it is P implies Q and Q implies P. So in the conditional, P implies Q. When you have if P then Q, another way to say it is P implies Q. In biconditional, P implies Q and the other way around is true too. That's why you have the double-sided arrow there, right? And in mathematics, soon you will start proving biconditional statements. And the way you prove them, one of the ways that you can prove them, most organic, intuitive, and user-friendly way to prove biconditional statements in mathematics is to use this double-sided idea. First, prove P implies Q, if P then Q, so one-sided conditional. Then go other way, backward, right? First forward and backward, reverse it, and prove if Q then P. And if you've proven both sides, then you've proven that biconditionality or if and only if condition. Okay, so much to look forward to. All right, so that is all I'm going to say about conditionals and biconditionals. I will simply now add two terms, converse and contrapositive. But for that, I need you to go back to conditionals. All right, so conditional statement was if P then Q. And converse of that is if you flipped the arrow, right? So instead of going from left to right, it now goes from right to left. And you can't do that. This is going to be false. It's not equivalent to the original statement. Because if it was, then it would be biconditional, right? Biconditional goes both ways. Conditional doesn't. Usually the backward is not going to be true. Another thing, a memory tip here. This might help you. The way that I first remembered when I learned it was that Converse shoes, they have crisscross or cross laces. So to create Converse statement, you just swap the places of P and Q, like you do X, like that. So maybe that helps you. Contrapositive, on the other hand, is always true. It's exactly equivalent to the original statement. You still have to swap the places of Q and P, but as contrapositive suggests, you're going to do not, okay? So contra is no. So you're going to put negation in front of them. So you swap the places, so you have Q, then P now, but contrapositive says not Q, then not P. So you will see in the next video more clearly, because these things are best done with pen and paper in a walkthrough or application video, where you will see that the truth tables of the original statement, if P then Q, are identical to if not Q, then not P, right? Because you follow the truth values and see where they go, and they lead you where they lead you, right? So thank you so much for watching. I hope this was helpful. This was all I'm going to say about conditionals, biconditionals, converse, and contrapositive. See you in the next video. Bye.